This is our lab 1. My name is Abang Alto Keberusan. My meeting number is 1, 2, 3, 4, 5.
My name is Ramana. Number 3. 1, 4, 2, 3, 9. Okay, my name is Nuria Nuria Azman. Number metric 1233291.
Now we are doing our lab session for microp.
So this is the result. Later we will show you all our solutions of class 1, class 2, class 3, class 4 and class 5.
The objective of this lab is to use the Microchip Studio Integrated Development Environment IDE to construct assembly language code. So basically in this lab, we will learn how to write the code and create the program using the assembly language. We also use the tools like practicing the writing, simulating and also debugging our code within the specific Microchip Studio IDE. And then we also need to verify our result by run the code and carefully examine the output like changes in register and also the memory to confirm that our code is working.
For the tool description, we use Microchip Studio and Advanced Start. So Microchip Studio is a professional software tool to write, debug and program microchips microcontroller such as the AVR family, which is Atmega 328P, Tiny AVR and Mega AVR, and the ARM-based SAM family. So next is the Advanced Start. Advanced Start is a web-based tool that automatically generate code and configurations for microchips, AVR and SAM microcontrollers. So specifically for this lab, we use the device Atmega 328P. So for the advantages, so Microchip Studio works with Advanced Start in initialization of a new project, and it has a reduced initial learning curve for complex peripherals, and the code is consistent and easy to maintain, and there are software libraries that are available and integrated in Microchip Studio which are supported. So for the disadvantages, the new layer of complexity it introduces a new layer of complexity as Advanced Start is a convoluted tool to learn and also generate code bloat, which make the code generation much larger than needed. And also the lock of specific vendor of code, which means it's exclusively for the Microchip Studio IDE frameworks, and also have a need to switch between both Advanced Start and Microchip Studio, which introduces disruptive workflow. So for the setup of Microchip Studio, first we download the tool, we make a new project from file, new project. The arrow key means from the file we click new and we click project. So for number 3 is we select the assembler and write the file name for the project. So in the device selection, we use Atmega 328P, and the Microchip Studio is open with view tab after the device selection, and there are main.asm window tab which we write the assembly code and other tabs also. So in the main.asm window tab, we go to build solution, or we use F7 button. Next is the enter debugging mode by selecting breakpoint on the left of assembly code. So for the 8, we go to debug, start debugging and break and choose simulator. Then again we go to debug, start debugging and break to start checking the code. So that's all for the setup of Microchip Studio.
So for problem 1, we store the 7 values into RAM starting at address 0 by 100. We use LDI because LDI can load an immediate constant directly into a register. So that's why we wrote LDI R16 1, LDI R17 2 and so on until LDI R22. So after the register holds the value, we use STS to store them into the data memory because STS allows us to write the value the register value straight into the specific RAM address. So STS 0 by 100 R16 puts the value 1 into the address 0 by 100, and then the rest is follow the same pattern. So when we step through the code in the debugger, we can see that the register being loaded and the data memory window show the final correct result. So this confirms that our problem 1 is successful. Okay, next for problem 2, we focus on instruction that can handle the data in memory. So we start by using LDI instruction twice. First, we use the load immediate value, which is 19 into register 16, and then LDI 20 into register 17. So this register now hold our initial value. So next, we adding the content R17 to R16, which can result in 39. So this sum is immediately stored back into R16. So finally, we use the STS to save the result in the microcontroller RAM. So STS 0 by 100 R16 stored the calculation 39 that I mentioned into the data memory address 0 by 100, and STS 0 by 101 R17 stored the value 20 into the address 0 by 101. So this task is successful.
So next, for this problem, first, the program loads initial values into the register R16, R17 and R18. R used as counter and temporary storage. Then, inside the loop, label again the instruction sub R1, R2, subtract the value in R2 from what R1. Every time the subtraction happen, the loop counter R18 decrease by 1 using DEC decrement R18. The instruction BRNE again, check if R18 is already 0. If not 0, the program jump back to the label again and repeat the subtraction. Since R18 start at the value 20, the loop will repeat exactly 20 times. That means the subtraction instruction runs 20 times before the program exit the loop. Okay, for problem 4, this program is used to calculate the sum of number from 15 down to 1 using a loop. So firstly, the program load the initial value into the register. R16 is set to 0 because the register will store the total sum. Then R17 is loaded with the value 15, which is the starting number we want to add. Next, the loop begins. Inside the loop, the instruction add R16. R17 will take the current number in R17 and add it to the total in R16. After adding, the instruction DEC R17 decrease the value in R17 by 1. So it goes from 15 to 14 to 13 and so on. So then the BRCS loop instruction tells the program to repeat the loop as long as R17 is not equal to 0. So the loop keep running until R17 becomes 0. Once R17 reaches 0, the loop stops and the final answer, which is the total sum of 15 plus 14 plus 13 until 1, is stored in R16. Finally, the program ends with the NOP instruction so that this could use a simple loop to add number from 15 down to 1 and stores the total in R16. Lastly, for the problem 5, this code works by using a loop to repeatedly add a series of number. So at the start, register R16 is set to 5, which is the first number we want to add. R17 is set to 0 to store the total sum. And for R18 is set to 6 because we want the loop to run 6 times to add. So then inside the loop, we add R16 into R17. So R17 keeps the running total. Then R16 is increased several times to move to the next multiple of 5. After that, R17 is decreased to control how many times the loop runs. Then the BRNE instruction check if R70 is 0. If not, it repeat the loop. So that this loop keep adding value like 5, 10, 15, 20, 25 and 13 until the total sum is complete.